Right. Diving in today, folks, we're going deep, deep into the world where artificial intelligence and FPGAs collide. You guys sent in a really amazing collection of articles and reports on this topic. And we're ready to sort of break it down for you. It's complex stuff.
Yeah, it really is. It's exciting, but there's a lot to unpack.
So just for starters, maybe for those listening who aren't, chip designers, what's the fundamental thing about FPGAs that makes them so important, especially when we talk about, AI and how quickly it's evolving?
So FPGAs, they're kind of like the chameleons of the chip world, They're not stuck in one configuration like the processors in your phone or laptop. You can actually reprogram them. So as AI algorithms change, and they do all the time, you can adapt the hardware without having to, physically swap out chips.
Right. So it's this reconfigurable nature that makes them so powerful in this world where things are changing so fast. Because if you had to build new hardware every time there was a breakthrough, we'd never keep up, right?
Exactly. You'd be stuck in the stone age of AI hardware.
Yeah, no kidding. So traditionally, this process of actually designing for FPGAs, telling them what to do, it's been pretty complex, right? It involves specialized languages, these hardware description languages.
Yeah, very specialized. VHDL, Verilog, these are not your everyday programming languages. And then you've got all these electronic design automation tools, EDA tools. Powerful, but definitely not something you pick up over a weekend.
It's a whole field of expertise in itself, really.
Absolutely. Years of study, lots of experience, not for the faint of heart.
So to get a handle on this, maybe let's walk through the basic steps. What does this FPGA design flow actually look like?
Okay, so imagine you're an engineer. You have an idea for some amazing function you want to implement on an FPGA. First, you nail down the specifics, the exact behavior you want. That's your specification.
Got it. The blueprint.
Yeah, exactly. Then you translate that blueprint into, one of those hardware description languages like VHDL or Verilog. That becomes your design entry. That code then goes through this crucial process called logic synthesis. And after that comes place and route, then rigorous verification to make sure everything works, and finally you generate the bit stream.
The bit stream, that's like the final set of instructions, right?
Yeah, the configuration file that actually tells the FPGA how to connect all its internal circuitry to make your design come to life.
Okay, so logic synthesis, that sounds kind of like, I don't know, alchemical or something. What's actually happening at that stage?
Yeah, it can feel that way. Basically, you're turning your high-level language description, your VHDL code, let's say, into a really detailed plan for the FPGA's hardware. This plan is called a netlist. It's basically a big map of how all the logic gates, the flip-flops, all the tiny components inside the FPGA need to be connected to do what your code describes.
Oh, I see. So it's like taking this abstract idea and making it concrete, turning it into a wiring diagram for the actual chip.
Exactly. And the synthesis tools are doing a lot of heavy lifting here, like figuring out how to break down complex operations into simpler ones the FPGA can handle, pulling in pre-designed modules, and crucially optimizing the whole thing to use as few resources as possible and run as fast as possible.
Right, because efficiency is always key, especially with these limited resources on the chip.
Absolutely. You want to squeeze every ounce of performance out of that silicon.
So who makes these powerful synthesis tools? Who are the big names in this space?
Well, you've got the FPGA vendors themselves, AMD, which acquired Xilinx. They have their Vivado design suite. That includes a tool called XST, which is an older one, but still widely used. Then there's Intel with Quartus Prime. Both of these have very capable synthesis engines built right in.
Right. So if you're working with, Xilinx or Altera FPGAs, you've got those tools right there.
Right at your fingertips. But then there are also dedicated EDA companies like Synopsys. They're huge in this space. They have tools like Simplify and Design Compiler FPGA. And Lattice Semiconductor, they offer Diamond and Radiant.
So lots of options depending on your specific needs.
Yeah, for sure. Though it's worth pointing out that even with these amazing tools getting the very best results, the most optimized design often still requires a lot of human expertise.
So it's not quite push-button automation yet.
Not quite. Experienced engineers know how to write their code in a way that these tools can really understand, how to set the right constraints, how to guide the synthesis process to get that extra bit of performance. It's still very much a partnership between human and machine.
Okay, so you've got your net list, your detailed plan for the chip. What happens next?
Place and route. And this is where things get, really intricate.
Place and route, it sounds, almost like urban planning or something.
In a way, yeah. So you've got this huge interconnected network of logic gates from the synthesis stage. Now, the place and route tools have to decide exactly where each of these blocks is going to sit on the physical chip, the actual silicon. And then they have to figure out how to run all the wires, the interconnects between them.
And this is happening at a microscopic scale, right?
Absolutely. We're talking nanometers here. It's like designing a super complex city on, I don't know, the head of a pin.
Wow.
So to tackle this problem, they use a bunch of clever algorithms. Simulated annealing, for example. It's like shaking a box of puzzle pieces and seeing if they fall into place better. Then there are min-cut algorithms, analytical methods, even genetic algorithms that sort of evolve solutions over time.
So it's like a whole toolbox of computational strategies.
Exactly. And the goal is to find the absolute best arrangement, the one that minimizes the length of all those wires, because shorter wires mean faster signals, right? And also avoid congestion, make sure all the connections can actually be made without, like, running into traffic jams.
And I imagine the FPGA vendors have their own specific tools for place and route, too, right?
Absolutely. Those are tightly woven into Vivado and Quartus Prime. It's a critical part of the whole flow.
Okay, so we've synthesized our design, figured out the physical layout. We're almost there, right?
Almost. But now comes the crucial step of verification. We have to make absolutely sure that this design, this complex arrangement of logic gates and wires, actually does what it's supposed to do, that it meets the original specs.
Right, because a tiny error at this stage could mean a whole lot of wasted time and effort, right?
Absolutely. You don't want to find out your chip has a bug after you've already manufactured it.
So how do they actually go about verifying these complex designs? What does that process involve?
There are a few key strategies. The most common is simulation. You basically create a virtual test environment, a software model of the FPGA and all the surrounding components, and then run your design through different scenarios, different inputs, and see how it behaves.
Like a virtual test drive for your hardware.
Exactly. Then there's formal verification. This is super rigorous. It uses mathematical proofs to check certain properties of your design to make sure it's logically sound.
So it's not just seeing if it works for the test you've thrown at it. It's proving that it must work under certain conditions.
Exactly. It's like a higher level of certainty. Then you have things like hardware-in-the-loop testing, where you run your design on a real FPGA but connect it to a simulated or even a real-world system to see how it behaves in a more realistic environment. And finally, there's emulation, which uses specialized hardware to speed up those simulations because they can take a long time.
Okay, so it's a multi-layered approach to catching those pesky bugs. And what are some of the go-to tools for verification?
Well, for simulation, there's ModelSim, QuestaSim. Those are very popular. And again, Vivado and Quartus Prime, they have their own simulation environments built in. For formal verification, you have tools like Jasper Gold and VC Formal.
So a whole arsenal of tools to make sure everything's working as intended.
Exactly. And it's worth mentioning that a big challenge in verification is achieving what's called comprehensive coverage. You have to make sure you've tested enough different scenarios, enough edge cases to be really confident that your design will work flawlessly in the real world. That's not always easy, especially with these increasingly complex designs.
Right, because the more complex it gets, the more potential hiding places for bugs. So we've walked through this traditional FPGA design process, and it's intricate, it's specialized, it involves a lot of expertise. But you mentioned there are some trends emerging that are trying to make it more efficient, more streamlined.
Yeah, exactly. We're seeing a big push towards higher levels of abstraction, making the process more accessible, more productive.
Okay, so what are some of the key ideas driving this shift?
Well, one of the most promising is high-level synthesis, or HLS for short. The basic idea is to let designers describe their hardware in more familiar, higher-level languages like C or C++C.
So instead of wrestling with those very specialized hardware description languages, you can use languages that are, well, more widely used and understood.
Exactly. And then specialized tools automatically translate that C or C++ code into the lower-level HDL code that the FPGA tools need.
So it's like having a translator between the high-level concept and the nitty-gritty hardware implementation.
Right. Another big trend is IP-based design. IP stands for intellectual property. It's basically the idea of reusing pre-designed, pre-verified hardware blocks. So instead of reinventing the wheel every time, you can pull in these ready-made modules for things like, memory controllers, communication interfaces, all sorts of common functions.
Like building with Lego blocks instead of starting from raw materials every time.
Exactly. It can save a ton of time and effort. And then you've got cloud-based development environments, which allow for more flexibility, more collaboration, and even the principle principles of agile development, the idea of iterative design and continuous feedback, that's starting to find its way into the hardware world.
So it's really a convergence of a lot of trends aimed at making this whole process more efficient, more agile.
Exactly, because the complexity is only going to increase, right? So we need better tools, better methodologies to keep pace.
And this is where AI starts to enter the picture, right? As a potential way to not just improve these existing methods, but maybe even completely revolutionize the way we design FPGAs.
Absolutely. And it's not a brand new idea, using AI and EDA, but the recent progress in machine learning, especially deep learning, has really opened up a whole new realm of possibilities.
Okay, so AI is moving into this FPGA design space. What are some of the specific types of machine learning that are relevant here, and how might they be applied to the different stages of this design process that we've talked about?
So there are a few key players. Supervised learning, that's where you train an AI model on labeled data where you already know the outcome. This is great for tasks like predicting how much of the FPGA's resources a particular design will use or how fast it will run.
So it's like giving the AI a bunch of examples and letting it learn the patterns.
Exactly. Then there's unsupervised learning. This is about finding hidden patterns in data where you don't have those predefined labels. This could be really useful for exploring the huge space of possible design choices and finding optimal solutions that, well, humans might not easily spot.
So it's like letting the AI go on a treasure hunt through all the possible designs.
In a way, yeah. Then you have reinforcement learning. This is where the AI learns through trial and error. You give it a goal, you let it take actions, and it gets rewarded or penalized based on how well it does.
So it's kind of like training a dog, but for hardware design.
Haha, kind of. This is especially promising for complex optimization problems like place and route, where there's so many variables and it's really hard to find the best solution using traditional methods. And then, of course, there's deep learning, which uses these very powerful neural networks to learn even more complex patterns and relationships in the data.
Deep learning, that's the one that gets all the headlines these days.
Yeah, for good reason. It's been incredibly successful in so many fields, and it's starting to make its mark in FPGA design as well.
So are we already seeing real-world applications of these AI and ML techniques in FPGA design today? Or is this mostly still in the research and development phase?
It's definitely moving beyond just research. We're seeing real applications in several key areas. One of the most impactful is using machine learning to improve those optimization algorithms that are used during logic synthesis, place, and route.
So AI is helping to make those crucial steps even more efficient.
Exactly. For example, Synopsys Design Compiler FPGA, it uses what they call adaptive optimization technology. It basically uses machine learning to pick the best synthesis algorithm based on the specific characteristics of the design you're compiling.
So it's like a smart toolbox that knows which tool to use for each job.
Exactly, and there's a lot of research happening in using Bayesian learning to automatically tune the parameters of those FPGA CAD tools, all those knobs and dials that control how they work to achieve specific goals. What's really amazing is that these machine learning algorithms, they can figure out complex relationships between design choices and their impact on performance, on resource usage, in a way that humans just can't.
So it's like the AI is learning to be a better designer than us.
Well, it's certainly learning to be a very powerful assistant, that's for sure.
Okay, that's really interesting. What about earlier in the design process, like being able to predict how many resources a design will need before you even get to the detailed implementation? That seems like it would be incredibly useful.
It's absolutely crucial, and that's another area where AI is showing a lot of promise. They're building machine learning models that can predict how much of the FPGA's, lookup tables, LUTs, flip-flops, DSP blocks, and on-chip memory you'll need just by analyzing a high-level description of your design.
Wow, so you can get a really good estimate of the cost, so to speak, before you even start building.
Exactly. And there are some great examples of this. The HLS 4LMEL workflow, which is used for designing custom AI accelerators on FPGAs, they've built resource estimators that can analyze your AI model and tell you how many LUTs, flip-flops, etc. it will need. And there's another open source project called Rule 4ML that uses HLS 4ML to actually train these predictive models, not just for resource usage, but also for the latency, the time it takes for the neural network to process data on the FPGA.
So you can get a sense of both how much space it will take up and how fast it will run.
Yeah.
That's incredibly powerful for for making early design decisions.
Absolutely. It lets you quickly assess the feasibility of your ideas and make adjustments before you invest a ton of time in detailed implementation.
That's a huge advantage.
Yeah.
And it sounds like AI is even being explored to make FPGAs themselves more reliable in operation.
Yeah, that's another exciting area. They're using AI for fault detection, both within the FPGA hardware itself and in systems that use FPGAs.
So it's not just about designing better FPGAs, it's about making them work better in the real world.
Right. For example, there's research on an FPGA-based system for detecting faults in railway infrastructure. It uses convolutional neural networks to analyze images of the tracks and identify potential defects. And there's work on using AI to detect errors in cryptographic computations running on FPGAs.
So it's really about using AI to enhance the reliability and security of these systems.
Exactly. The idea is that AI can learn the normal operational patterns of the FPGA and then quickly identify any deviations or anomalies that might indicate a problem.
That's a really powerful application. Now, some of the stuff you shared talked about this idea of autonomous hardware generation. That sounds almost like something out of science fiction. What does that even mean in the context of FPGA design?
Yeah, it's definitely an ambitious vision, but it's something that researchers are actively pursuing. And one of the key aspects is taking high-level synthesis, that idea of describing hardware in a high-level language, to a whole new level.
So instead of just translating from C++ to HDL, you're talking about AI actually generating the HDL code from scratch.
That's the ultimate goal. Imagine being able to describe what you want the hardware to do in natural language, like plain English, and then have the AI generate the optimized Verilog or VHDL code for you.
Wow, that would be a game changer. No more wrestling with those arcane hardware description languages.
Right. And AI could also take over a lot of those tedious tasks in HLS, like finding the absolute best compiler settings to achieve specific performance goals. The idea is to free up human designers to focus on the high-level functionality, the big picture, and let the AI handle all the low-level details.
So you're essentially shifting the role of the human designer from coding to, more like directing or orchestrating.
In a way, yeah. And another really fascinating direction is using AI to optimize not just the design, but the very architecture of the FPGA itself.
So not just designing for a fixed chip, but designing the chip itself.
Exactly. They're exploring techniques like Bayesian optimization to discover the ideal structure for the FPGA for specific applications like AI acceleration. Intel's FPGA AI suite is a step in this direction. It gives you tools to explore different architectural configurations for AI inference.
So it's like AI designing the very hardware that will run AI. That's pretty mind-bending.
Yeah, it's really getting into this recursive loop of AI enhancing itself. And then there's this, holy grail of actually generating HDL code from scratch, from a high-level spec.
It's really taking the human out of the loop completely, at least at the coding level.
Right. And there's some really interesting research happening here. They're using these large language models, the same kind of technology behind things like ChatGPT, but training them on HDL code and using them to generate Verilog or VHDL.
Yeah.
And they're using these things called paradigm blocks, which are basically like pre-designed templates that capture best practices from human experts to guide these language models and make sure they generate code that's actually correct and efficient.
So it's like giving the AI a set of building blocks that it can then assemble in creative ways.
Exactly. And it's still early days, but the potential is huge. If we can crack this, it could dramatically speed up the whole hardware development process.
And if AI is generating the hardware, it seems natural that it could also play a big role in verifying that the hardware actually works correctly.
Absolutely. AI-driven verification is a very hot area of research. They're using AI to automate test case generation, creating those test scenarios that we talked about. They're using AI to analyze simulation results and pinpoint the root cause of errors to help with debugging. And they're even using AI to enhance those formal verification techniques to make them more scalable and applicable to these really complex designs.
So it's really about using AI to make the whole verification process more efficient, more thorough, and ultimately to make the hardware more reliable.
Exactly. And that's a huge win because verification is often a bottleneck in the whole design process.
Right. Okay, so this autonomous FPGA design future, it sounds incredibly exciting. But surely there's some pretty significant challenges that need to be overcome before we get there.
Yeah, for sure. It's not all smooth sailing. Well, one of the biggest challenges is just the sheer complexity of modern FPGAs. These chips have millions, even billions of transistors, a vast array of configurable logic blocks, a mind-boggling number of interconnections. It's a huge design space for even the most powerful AI to navigate.
Where it's like trying to find the perfect grain of sand on a beach.
In a way, yeah. And it's not just about finding a solution, it's about finding the optimal solution, the one that uses the least resources, runs the fastest, consumes the least power.
And with AI generating the hardware, how do we make sure that the designs are actually correct, that they're reliable, that they'll work as intended in the real world?
That's a huge question. It's one thing for AI to come up with a design that passes some basic tests, but it's another thing entirely to be confident that it will work flawlessly under all conditions, in all the different environments it might be used in. And while AI is getting better at things like formal verification and test generation, it's still not at the level where we can just blindly trust it to produce perfect hardware.
So there's still a very important role for human expertise in this process, right?
Absolutely. Humans are still needed to set the high-level goals, to define the specs, to make sure the AI is solving the right problem, and to ultimately validate the designs that the AI produces, especially for novel applications. For cutting-edge stuff where there aren't a lot of existing examples to learn from, human intuition and creativity are still essential.
It's like the AI is a powerful tool, but it still needs a skilled craftsperson to wield it effectively.
A good analogy. And another big challenge is data. Machine learning algorithms, they're only as good as the data they're trained on. And in the world of FPGA design, there isn't a lot of publicly available high-quality data. Companies tend to keep their designs and their verification results pretty close to the vest.
Right, because that's their intellectual property, their competitive advantage.
Exactly. So building really effective AI models for FPGA design is tough because we just don't have access to the huge data sets that are driven progress in other areas of machine learning.
It's like trying to teach someone to cook without letting them see any recipes.
Haha, kind of. And then there's the issue of the FPGA vendors themselves and their proprietary tools. The details of those tools, the specific architectures of their chips, it's all pretty tightly controlled.
So it's hard for independent developers to come in and build these, truly universal AI-driven design flows.
Right. It's kind of a walled garden situation. And then finally, there's just the sheer computational power needed to train and run these complex AI models. We're talking about some serious computing muscle.
Right. Not everyone has access to a supercomputer in their basement.
Exactly. So making these AI-driven tools accessible to a wider range of users, to smaller companies, to researchers, that's a challenge too.
Okay, so there are definitely some hurdles to overcome. But even with those challenges, it's clear that AI has a potential to really transform this whole field of FPGA design. What are some of the broader impacts you see as AI becomes more deeply integrated into this world?
Well, one of the most significant will likely be a dramatic reduction in design cycle time. AI can automate a lot of those tedious, time-consuming tasks that humans currently do, which could lead to much faster product development cycles.
So companies could get their FPGA-based products to market much faster.
Exactly. And that could have huge implications for innovation in all sorts of fields that rely on FPGAs, from, aerospace and defense to telecommunications and, of course, AI itself.
And what about the engineers who are currently designing FPGAs? How do you see their roles evolving in this AI-driven future?
I don't think their jobs are going away anytime soon, but their roles will definitely change. As AI takes over more of the low-level design work, engineers will likely shift their focus to higher-level tasks like defining system architecture, setting design goals, making sure the AI is solving the right problems.
So it's like they become more like architects or conductors guiding the AI rather than doing all the detailed coding themselves.
Exactly. It'll require a different set of skills, more emphasis on systems thinking, on collaboration with AI, on understanding the big picture.
And it seems like this could also open up the possibility for creating much more specialized, more customized hardware solutions.
Absolutely. AI has the potential to design hardware that's perfectly tailored to a very specific task, to a particular algorithm, to a unique set of constraints. This could lead to much more efficient, more powerful solutions than we can achieve today with, general purpose processors.
So it's like having a custom-made suit instead of buying one off the rack.
A perfect analogy. And this could be especially important in fields like AI acceleration, where the algorithms are constantly evolving and we need hardware that can keep up.
Right, because a one-size-fits-all approach to hardware just isn't going to cut it in a world where AI is becoming so specialized.
Exactly. And then there's the question of how FPGAs will fit into the broader landscape of AI hardware, alongside things like GPUs and ASICs.
Right, because those are the, the heavy hitters in the AI world right now.
They are, but I think FPGAs still have a very important role to play. GPUs and ASICs, They're great for raw processing power, but they're not as flexible. They're not as reconfigurable as FPGAs. And that flexibility is going to be increasingly important in a world where AI algorithms are constantly evolving.
So it's like GPUs and ASICs are like race cars. They're super fast,
Right.
but they can only run on a specific track. FPGAs are more like all-terrain vehicles. They can adapt to different environments.
A good analogy. And that adaptability is going to be crucial, especially in applications where power efficiency is key, like in edge devices, or where you need to be able to update the hardware in the field as the algorithms change.
So it's going to be a mixed ecosystem with different types of hardware playing to their strengths.
Exactly. It's not a winner-take-all situation. It's about finding the right tool for the job.
So just to sum up some of the key benefits of this AI-driven evolution in FPGA design, we're talking about potentially much faster design times, improved performance and power efficiency, the ability to create highly customized hardware, and maybe even a democratization of hardware design, making it more accessible to a wider range of users.
Yeah, those are some of the big promises. I think they're very realistic, but of course there's still a lot of work to be done, a lot of challenges to overcome.
Right, it's not going to happen overnight. So what are some of the things that the experts in the field are saying about where this is all headed? What are their predictions for the near term and the long term?
Well, some of the big EDA companies like Synopsys, they're pretty bullish. They're predicting that we'll see AI agents actively collaborating with human engineers in chip design as early as 2025. So that suggests a near future where AI is really embedded in the design process.
So not replacing humans, but working alongside them.
Right, like a co-pilot.
Yeah.
And then there's this longer-term vision of designers being able to describe their hardware requirements at a very high level, maybe even in natural language, and then have the AI generate the code.
So like talking to the AI and saying, I need a chip that can do this, and the AI spits out the design.
That's the dream, yeah.
Yeah.
But there are also more cautious voices out there, people who think that fully autonomous hardware generation is still a long way off, that FPGAs still have some challenges to overcome in terms of their programming model and the maturity of the software ecosystem.
Right, it's not all hype. There are real technical hurdles.
Absolutely. And there are also questions about how FPGAs will compete with those, more specialized AI chips, the GPUs and ASICs. But even with those more cautious perspectives, there's a lot of investment and activity happening in this space. The big FPGA vendors, they're all pouring resources into AI, integrating it into their tools, building AI-specific features into their chips. Even companies like Tesla, they're getting into the game, designing their own custom AI chips.
So it's clear that this is a trend that's not going away anytime soon.
Definitely not. It's only going to get bigger.
Well, this has been a really fascinating deep dive. I feel like we've covered a lot of ground from the nuts and bolts of traditional FPGA design to this really exciting and potentially revolutionary future where AI is playing a much bigger role.
It's an amazing time to be in this field, that's for sure. Lots of challenges, but also lots of opportunities.
And it leaves me with a question for you, the listener. As AI takes on more of the heavy lifting in hardware design, what new possibilities will that open up? What new applications will become feasible when we can create highly customized, highly optimized hardware much faster and more easily than we can today? It's really a question of how this technology will empower human creativity and ingenuity. So thanks for joining us on this journey. It's been a pleasure exploring this fascinating topic with you.